Hello there and welcome to The Sleepy Scholar. Tonight we are drifting into the quiet mystery of intelligence, a subject that sits at the center of every thought we have ever had. Intelligence is not only a human trait, it is a presence that appears in forests, in oceans, in animals with minds unlike our own, and even in the silent patterns that guide the universe. It is the strange ability to imagine, to solve, to adapt, and to create new possibilities from almost nothing. As you settle in, imagine intelligence as a hidden current flowing through everything, shaping life in ways we hardly notice. In some ways, it is familiar and comforting, and in others, it feels so strange that it changes how we see the world. It is one of science's greatest frontiers, and we are only just beginning to uncover its secrets. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest. Let your eyes relax. Allow your body to soften and let your mind drift gently into wonder. Let's begin. Intelligence may have emerged when early humans began to dream more vividly. In the deep nights of our early ancestors, long before writing or cities, sleep would have wrapped small bands of humans in darkness and vulnerability. Inside those resting bodies, the dreaming mind could roam freely, replaying past events and inventing scenes that had never actually happened. A hunter might relive a close call with a predator, but in the dream, the escape was smoother, the path clearer, the reaction faster. Over many nights, these silent rehearsals could refine instincts without the cost of real danger. Dreams blend faces, places, and emotions into strange new combinations. This creates a mental workshop where the mind experiments with social situations, future threats, and hidden opportunities. The individuals whose dream worlds offered better practice and richer imagination may have navigated the waking world with more foresight and subtlety. Over countless generations, those slight advantages could have helped shape the complex storytelling intelligence that humans carry today. The brain can rewrite its own wiring in a single night of intense learning. After a long day spent struggling with a difficult idea or a new skill, the brain does not simply rest. As you sleep, billions of connections quietly reconfigure, strengthening some pathways and weakening others. Neurons that fired together repeatedly during the day are more likely to build stronger links, forming roots that make future thinking smoother and faster. Intricate chemical signals adjust the sensitivity of synapses, the tiny gaps where one cell speaks to another. In deep sleep, the brain replays patterns of activity from waking practice as if running internal drills without conscious awareness. Even in a single night, this replay can carve new paths through the neural landscape, turning clumsy attempts into more fluent performance by morning. A piece of music feels easier to play. The pattern in data becomes clearer. A foreign phrase sounds more natural. The skull hides a restless city of cells, tirelessly editing yesterday into a better version of tomorrow. Some animals outsmart humans in tests designed by humans themselves. When scientists create puzzles to measure cleverness, they often expect human minds to sit at the top of the scale, yet certain animals quietly overturn that assumption. In tasks that require spotting subtle probabilities, pigeons choose the mathematically correct answer more consistently than many human volunteers who are swayed by hunches and stories. In visual memory challenges, some primates can recall the position of many symbols after a fleeting glimpse far beyond the recall of typical adults. These performances do not simply show quick reflexes. They reveal specialized strengths shaped by different evolutionary pressures tuned to specific environments and survival needs. While humans excel at language, metaphor, and long-term planning, other creatures shine in domains where precision, pattern recognition, or sensory detail matter most. The tests themselves, crafted by human hands, become mirrors that reflect our biases about what intelligence should look like. In those reflections, other species sometimes stand taller than we do. A tiny portion of the brain predicts your decisions before you become aware of them. Well, before you feel that moment of choice, a small network of neurons has already begun to lean toward one outcome. In regions that prepare movements and select actions, electrical activity gradually shifts, favoring one possibility while your conscious mind still feels undecided. This slow build-up of signal unfolding over fractions of a second reflects the accumulation of evidence, habits, and subtle preferences stored from many past experiences. By observing these patterns, researchers can often guess which option a person will select slightly before the person reports having made a decision. Conscious awareness then arrives like a narrator who steps onto the stage just after the main plot twist, explaining a choice that was already in motion. This does not remove the meaning of intention or responsibility, but it does suggest that what we call a decision is the visible crest of a much deeper wave of neural activity rolling forward beneath the surface of awareness. Intelligence rises when the brain learns to ignore most of reality. Every moment, the senses deliver far more information than any mind could fully process. Light floods the eyes. Vibrations press into the ears. Countless signals travel from skin, muscles, and internal organs. Intelligent behavior emerges not by absorbing all of this detail, but by discarding most of it. The brain quickly learns which patterns matter and which can fade into the background. It filters out the steady hum of a fan, the constant pressure of clothing, the repetitive shapes in a familiar room. By compressing and simplifying, it frees up precious resources to track changes, unexpected events, and meaningful relationships. The art of ignoring becomes a powerful cognitive tool. Minds that excel at this filtering can build cleaner internal models of the world. Models that focus on cause, consequence, and opportunity rather than raw sensation. In that focused inner space, complex reasoning, planning, and creativity can rise above the noise. Certain octopuses can solve puzzles they have never seen before. In the dim water of an aquarium or the shifting light of a reef, an octopus encounters a closed container that smells faintly of food. No one has shown it how to open the device. Using flexible arms lined with sensitive suckers, it explores every edge, hinge, and surface. In some species, this exploration turns into remarkably fast problem-solving. The animal discovers how to twist a cap, slide a latch, or pull a plug with movements that reveal more than instinct. Each arm can test different approaches, feeding information back to a nervous system that is distributed rather than centralized. Much of its neural tissue lies outside the main head region, as if parts of its body think locally while still contributing to a shared goal. When the container finally opens, the solution represents a moment where tactile memory, curiosity, and flexible control converge. The result is a display of intelligence that developed along a path entirely separate from the vertebrate mind. Your brain generates ideas by mixing signals that were never meant to touch. Inside the skull, networks that evolved for very different purposes constantly interact. A region that once guided hand movements now participates in abstract reasoning about tools. Areas that track space and movement contribute to the way you navigate social situations and numbers. When you relax and let thoughts drift, activity in distant regions begins to synchronize, linking emotional memories with factual knowledge, sensory images with language, and past experiences with imagined futures. Signals spill across boundaries, meeting in association areas that act like busy crossroads. There, unrelated fragments collide in patterns that normally never appear together. From those collisions, new ideas can emerge, like sparks from stones striking at odd angles. A creative insight often feels sudden, but underneath that feeling lies a slow, rich mixing of neural streams that were originally tuned for separate tasks. The mind turns this accidental meeting of signals into deliberate invention. Some trees use chemical messages so sophisticated they resemble primitive thought. In a quiet forest, a single tree detects the bite of an insect on its leaves. Within moments, chemical changes begin, producing bitter compounds that make the foliage less appealing. At the same time, airborne molecules drift outward, carrying information about the attack. Neighboring trees of the same species sense these signals and adjust their own defenses as if they have received a warning about an invisible danger. Underground, roots form partnerships with fungal networks that transfer nutrients and signaling compounds across long distances. Through these shared pathways, a tree that is struggling can receive resources from others that are thriving, or send out distress cues that alter the behavior of its companions. The timing, specificity, and context-dependent nature of these exchanges create patterns that look strikingly like problem-solving. Without neurons or a central brain, the forest still manages to gather information, spread it, and respond in ways that benefit the community. The brain simulates entire futures in the time it takes you to blink. Before you step off a curb, reach for a handhold, or open your mouth to speak, internal models of possible outcomes flash into existence. In brain regions that handle memory and spatial navigation, patterns of activity sweep through imagined paths faster than your body could ever move. The mind rapidly tries out different sequences, predicting where obstacles might appear and how other people might respond. Most of this work happens outside awareness, compressed into moments so brief that they feel instantaneous. When you finally act, the choice carries the imprint of many invisible rehearsals. The same machinery supports more abstract planning, allowing you to picture career changes, relationships, or creative projects unfolding over months or years, all within a brief daydream. By running these compressed futures, the brain lets you harvest some of the benefits of experience without enduring every risk. Each action you take carries echoes of countless unrealized possibilities that lived for only a heartbeat inside your head. Human intelligence may depend on neurons that fire in beautifully imperfect patterns. If each neuron responded to inputs in a rigid, repetitive way, your mind would behave like a perfectly wound clock, accurate but predictable. Instead, neural firing is full of subtle variability. Cells sometimes respond strongly to a signal, sometimes weakly, and sometimes not at all, even when the stimulus appears nearly identical. At first glance, this looks like noise, an annoying flaw in a delicate system. Yet, this irregularity can enlarge the space of possible responses, allowing the brain to represent shades of meaning rather than simple yes or no categories. Networks of such cells can explore many internal states while still remaining stable enough to function. In this flexible regime, small changes in experience can nudge patterns of activity toward new configurations that encode fresh insights. The mind gains the capacity to generalize, to handle ambiguity, and to combine ideas in unprecedented ways. Intelligence grows not from perfect precision, but from structured imperfection woven through the firing of countless cells. Bees can recognize human faces with a brain smaller than a grain of sand. In a busy garden filled with shifting colors and moving petals, a bee must quickly separate friend from foe, flower from distraction. Despite having a brain smaller than a grain of sand, this tiny creature can learn to distinguish individual human faces with surprising accuracy. It does this not by seeing a face the way humans do, but by breaking the image into a pattern of shapes, edges, and contrasts, then storing the overall configuration as a kind of visual signature. When the same person appears again, the bee can match that signature to its memory and respond accordingly. This ability emerges from an incredibly efficient neural system that uses only a few thousand specialized cells to encode complex images. Instead of processing every detail, the bee focuses on the most informative features, creating a lean and powerful method of recognition. This reveals that intelligence does not depend solely on size. It can arise from elegant design, minimal waste, and the ability to extract meaning from the smallest fragments of perception. Your brain predicts the world before it sees it and calls the mistakes reality. In every waking moment, the brain constructs a silent guess about what will happen next. Before a sound reaches conscious awareness, or before a shape becomes fully visible, internal models begin to anticipate the world. These predictions come from memories, expectations, and patterns learned over a lifetime. When the incoming sensory information finally arrives, the brain compares it to its own forecast, blending the two until they match closely enough to feel seamless. Most of the time, this process creates a smooth and efficient experience, letting you move through life without pausing to interpret every flicker of light or shift in sound. Yet, the guesses are not always correct. The brain fills in missing details, invents edges that are not really there, and smooths over contradictions that might otherwise feel jarring. This delicate merging of expectation and perception shapes what you believe to be real. Your sense of the world is not a raw recording. It is a refined story built from constant predictions. Dolphins invent new whistles to name ideas they have never encountered. Within the shimmering blue corridors of the ocean, dolphins communicate through whistles that curve and ripple like underwater melodies. These sounds are not simple signals. They have structure, rhythm, and variation that reflect an astonishing level of flexibility. Dolphins can improvise new whistles when faced with new situations, creating custom acoustic shapes that stand for unfamiliar objects, unique individuals, or novel experiences. In social groups, these invented sounds spread as companions learn to interpret them. Each whistle becomes a bridge between thought and expression, allowing the animals to share information with remarkable nuance. The ability to generate symbolic sounds emerges from a brain that evolved for cooperation, hunting coordination, and complex social bonds. Dolphins must understand shifting dynamics within their pods, track relationships, and respond to subtle cues in real time. Their expanding vocal repertoire acts as a cognitive toolkit, allowing them to form new associations whenever the world presents something unexpected. The mind learns faster when it completely misunderstands something first. A paradox lies at the heart of deep learning. When the mind forms an incorrect assumption, it creates tension between expectation and evidence. That tension becomes fuel for rapid improvement. A misunderstanding exposes the boundaries of existing knowledge and forces the brain to reorganize its internal models. Neurons that once fired confidently in one pattern must now shift to accommodate new information. When the correction comes, it produces a sharper, more resilient understanding than if the mind had simply absorbed the idea without friction. This process appears in children who struggle with a concept before mastering it, in adults who confront a mistaken belief, and even in artificial systems that refine their predictions through repeated error. The initial confusion opens a cognitive space where new connections can form more freely. The mind becomes more attentive, more flexible, and more capable of forming insights that would not emerge without the spark of an early mistake. Ravens can plan several moves ahead without ever practicing the task. High on a windswept branch, a raven eyes a distant reward. To reach it, it must perform a sequence of actions that it has never executed before. Without trial and without guidance, the bird evaluates the objects available and selects the tool that will allow the latest steps to succeed. This ability reflects an inner simulation, a process in which the raven mentally rehearses events before acting. Rather than relying on instinct alone, it imagines how each object will behave, how obstacles can be overcome, and how its movements will interact with the environment. Such foresight requires an understanding of causality and physical principles that go far beyond simple learning. It reveals a mind capable of holding multiple possibilities at once, discarding the ones that lead nowhere, and choosing the one path that opens a new solution. In this quiet moment of planning, the raven demonstrates a level of reasoning that rivals much larger brains. Human creativity may come from neural noise that other species filter out. Inside the brain, signals do not flow with perfect order. Mixed within the purposeful firing of neurons is a layer of irregular activity that seems random at first glance. Many species suppress this internal noise to achieve precision and efficiency. Humans, however, appear to preserve a portion of it. This gentle chaos creates opportunities for unlikely connections to form, letting ideas that normally stay separate drift close enough to combine. A stray memory may collide with a sensory impression. A half-formed image may merge with a mathematical concept. These encounters generate new possibilities, often without conscious effort. When attention relaxes, the noise grows louder, allowing the mind to wander through a wider landscape of thoughts. Over time, structured patterns emerge from that wandering, giving rise to metaphors, inventions, stories, and imaginative leaps. Creativity becomes the art of shaping this controlled turbulence into something meaningful. Elephants comfort distressed herdmates with behaviors that resemble empathy. In a savanna shimmering with heat, an elephant senses agitation in a companion. Without hesitation, it approaches with deliberate calm. The touch of a trunk across the face or shoulder carries a soothing pressure. A soft rumble vibrates through the air, a sound tuned to reassurance. Others may gather, offering quiet presence rather than forceful action. These responses arise from an understanding of emotional states within the group. Elephants track the mood of their herd, remembering past events that shaped each relationship. When one individual suffers fear, grief, or uncertainty, the others react with comfort that seems to emerge from shared feeling rather than simple imitation. This emotional intelligence supports the cohesion of their social structure, allowing families to endure hardship and protect vulnerable members. Their comfort behaviors demonstrate that the roots of empathy can grow in minds that evolved far from human experience, carried by memory, sensitivity, and deep relational bonds. Artificial intelligence models reveal patterns in nature that no human had imagined. Modern learning systems can sift through intricate data that spans oceans, climates, and ecosystems. While they do not think in a human sense, their ability to detect patterns creates new windows into the natural world. When given satellite images, they uncover hidden rhythms in the movements of forests, currents, and animal populations. When trained on astronomical measurements, they reveal relationships between distant stars and swirling clouds of dust that had eluded researchers for decades. These discoveries arise not from intuition, but from an unbiased search through vast spaces of possibility. By highlighting connections too subtle or too complex for a human mind to notice, these models expand our understanding of how life and the universe are organized. Their predictions become hypotheses that scientists can explore, grounding imagination in fresh evidence. In this partnership, human insight and computational analysis weave together new stories about nature. Parrots can understand abstract rules that even children struggle with. In the presence of colored shapes, objects of different sizes or patterns arranged in deliberate sequences. Some parrots show an ability to identify rules that are not tied to specific items. They can tell when two things match in a certain property, even when the specific examples change completely. This reveals a grasp of relationships rather than mere memorization. When asked to apply a familiar rule to an entirely new set of objects, these birds can extend their reasoning without hesitation. Their understanding emerges from a combination of social cognition, problem solving, and a natural curiosity that drives them to manipulate objects and explore cause and effect. These same traits support complex communication and deep bonds with flock members. As they navigate these social landscapes, their minds develop structures capable of handling subtle ideas. What looks simple on the surface reflects a sophisticated internal logic. Your brain stores memories by rewriting them in new forms every time you recall them. A memory is not a preserved photograph. Each time you reach for it, the act of retrieval changes its structure. The brain reconstructs the experience from fragments scattered across many regions, stitching sensory impressions, emotional context, and meaning into a single coherent whole. During this reconstruction, the memory becomes open to alteration. New details blend with old ones, interpretations shift, and the narrative takes on the shape of who you are in that moment. Once returned to storage, it carries these subtle revisions. This process allows memories to remain flexible, adapting to new understanding and new circumstances. It also means that the past is partially created by the present. Through this dynamic rewriting, the brain maintains a library that stays relevant to the challenges of life, rather than freezing experiences in rigid form. Squid neurons use exotic biochemistry that lets them edit their own genetic messages. In the dim water of the open ocean, squid rely on a nervous system built for rapid action, shifting color displays, and sudden bursts of movement. Their neurons use an unusual biochemical strategy that allows them to rewrite portions of their RNA, the molecules that act as working copies of genetic instructions. Instead of relying solely on the fixed information encoded in DNA, squid can adjust these RNA sequences to fine-tune how their proteins behave. This helps them respond to changing temperatures, shifting currents, and complex environmental pressures. Editing RNA on the fly gives them an adaptive flexibility that most animals lack. By altering the messages inside their cells, they can modify how electrical signals travel along their giant axons and maintain precise control over their fast-moving bodies. This remarkable ability reveals a form of molecular intelligence that operates beneath conscious awareness, a cellular system that adapts minute by minute to the fluid world around them. Music can restructure thought patterns in ways that increase spatial reasoning. When musical tones rise and fall in carefully arranged sequences, the brain forms patterns of expectation that synchronize activity across regions involved in timing, planning, and prediction. Listening to music can guide neural rhythms into orderly states that encourage more coherent thought. Over time, these rhythmic patterns influence how the brain processes relationships in space, such as rotations, distances, and geometric transformations. Practicing a musical instrument deepens this effect by training fine motor control, auditory discrimination, and working memory simultaneously. As these systems strengthen, they knit together more efficiently, allowing the mind to form clearer mental maps and track complex spatial structures with greater ease. This influence extends beyond the music itself. The structured flow of melody and harmony encourages the brain to explore new connections, supporting reasoning in fields such as mathematics and navigation. Music becomes more than sound. It becomes a quiet architect of cognition. Certain plants anticipate light cycles and change their growth before dawn arrives. Long before the sun rises, certain plants begin adjusting their orientation, metabolism, and internal chemistry. These shifts occur even in controlled environments where the timing of external light remains constant. The behavior emerges from internal clocks built into their cells. These track the passage of time through cycles of gene activation and suppression, creating rhythms that align with the turning of the planet. As dawn approaches, plants activate processes that prepare their leaves for photosynthesis. They adjust the opening of tiny pores, redistribute sugars, and alter growth hormones so they can gather energy more efficiently when the first light finally appears. This anticipation helps them survive in environments where every moment of sunlight matters. The precision of these internal rhythms reveals a quiet sophistication. Without nerves or brains, plants still sense patterns that extend far beyond immediate conditions. Your brain creates entire internal universes to test ideas before you speak them. Within the folds of the cortex, networks spring to life whenever you consider possibilities. As you prepare to express a thought, the brain generates internal simulations that play out imagined consequences. These mental spaces contain fragments of memory, sensory impressions, and abstract concepts arranged into miniature worlds where ideas can be tested without risk. When exploring a problem, the mind activates these internal landscapes, letting possibilities rise and dissolve before any words form. Each mental universe is shaped by experience, emotion, and knowledge. Yet, it remains flexible enough to support new combinations. In these quiet rehearsals, the brain evaluates meaning, adjusts phrasing, and settles on the version of the idea that best reflects your intention. Much of this process happens beneath awareness, giving the impression that thoughts emerge fully formed. In truth, each idea is the result of countless unseen trials. Crows understand the concept of zero as a meaningful quantity of nothing. In controlled experiments, crows distinguish between symbols representing different quantities, including the symbol that stands for none at all. They treat this absence of quantity as a real value, placing it correctly on a mental number line. When shown varying amounts of objects, they respond differently to the case where nothing is present, demonstrating an understanding that zero is not simply the absence of something familiar, but a distinct concept with its own place in a sequence. This insight requires a sophisticated mental framework that goes beyond simple counting. He reflects the ability to generalize rules about order and magnitude. In the wild, such reasoning may help them evaluate risk, track resources, or interpret subtle changes in their environment. Their grasp of zero suggests that abstract reasoning can emerge in minds shaped by evolutionary paths far from our own. Ant colonies act like distributed minds that solve problems no single ant could comprehend. Within a colony, thousands of ants follow simple rules based on pheromone cues, local interactions, and shared tasks. Yet, when these individual behaviors combine, the colony displays coordinated strategies that appear far more intelligent than any single ant. They regulate temperature inside their nests by adjusting airflow through complex tunnel systems. They find efficient foraging routes by allowing the most successful paths to gain stronger chemical signals. They defend against invaders using collective maneuvers that shift with the size and position of the threat. This emergent intelligence arises from distributed processing, where no leader directs the group. Instead, information flows through continuous movement, chemical exchange, and shared labor. The colony becomes a living network capable of flexible problem solving, adapting to challenges that would overwhelm isolated individuals. Human intelligence may have strengthened because our ancestors shared stories. In early human groups, storytelling shaped the way individuals understood the world. Around a fire, people described dangers, resources, alliances, and memories. These shared narratives allowed communities to accumulate knowledge that exceeded any one person's experience. Young members learned from the stories of the older ones, gaining insight into events they had never witnessed. Over generations, this cultural transmission created a collective memory that evolved alongside the genetics of the population. Minds that could craft clearer stories, interpret meaning from events, or imagine the experiences of others gained an advantage. Storytelling encouraged empathy, cooperation, and long-term planning, helping early humans coordinate hunts, form alliances, and navigate complex social dynamics. Intelligence became entwined with the ability to weave meaning into the arc of experience. Whales communicate through layered signals that function like multi-level languages. In the open sea, whale vocalizations travel across vast distances. These sounds contain multiple layers of structure, including repeating units, shifting patterns, and long sequences that can last for minutes or even hours. Some species combine basic elements into larger motifs, which then form extended songs that vary by region and social group. Individuals modify their calls in response to companions, adjusting timing, pitch, and rhythm. This layered communication system allows whales to coordinate movement, maintain contact, and convey information about identity and emotion. The complexity resembles early forms of language because the meaning is not tied to a single sound, but emerges from patterns arranged across time. Each population develops unique variations, creating dialects that shift gradually through generations. Their voices become both a practical tool and a cultural expression. The brain can learn patterns hidden so deeply that you never become conscious of them. Throughout everyday activities, the brain extracts regularities that lie beneath awareness. When exposed to sequences of sounds, images, or movements, neural circuits detect statistical relationships between events over time. These unconscious patterns influence behavior. You may sense the rhythm of a piece of music before recognizing its structure or anticipate the movement of a crowd without knowing why. This implicit learning shapes skills such as language, coordination, and social intuition. It allows the mind to adapt to environments too complex to analyze consciously. The process operates continuously, building internal models from countless tiny correlations. These models guide perception and action, even when the details remain hidden from conscious thought. The brain becomes a silent analyst, discovering structure in the world without deliberate effort. Some frogs navigate complex forest mazes using a sense researchers still cannot explain. Deep in dense forests where light filters through layers of leaves, certain frogs display an uncanny ability to find direct routes through complicated terrain. Even when paths twist unpredictably, they move with purpose, choosing turns that lead them efficiently toward shelter or water. Experiments attempt to isolate the cues they use, yet vision, scent, and sound do not fully account for their accuracy. These frogs seem to rely on a sensory system that remains mysterious. Their bodies might detect subtle gradients in humidity or electromagnetic fields, or perhaps they perceive spatial information through a mechanism hidden in their skin or inner ear. Whatever the source, the result is a form of environmental awareness that guides them through landscapes where human senses would filter. Their effortless navigation hints at undiscovered ways of knowing the world. Human problem-solving improves when the mind begins to wander. When focus softens and attention slips away from a stubborn problem, the mind does not truly switch off. Activity shifts into networks that connect distant memories, half-formed impressions, and forgotten details. This roaming state lets ideas move into new combinations that strict concentration often blocks. A passing smell can link to a scene from childhood. A sound can pull up a lesson learned long ago. While you fold laundry, walk a familiar path, or stare at the ceiling in the dark, the brain continues to reshuffle patterns beneath awareness. Possibilities that were previously invisible slide into view. An approach that felt impossible a moment earlier suddenly seems natural. This effect appears in artists, scientists, and anyone facing tangled choices. Wandering thought becomes a quiet workshop where new structures of understanding are built without effort. What looks like distraction from the outside becomes on the inside, a deep reorganization of how a problem is framed. Termite mounds behave like climate-regulating machines built by collective intelligence. Under intense sun and heavy rain, towering earthen structures rise from the ground, constructed grain by grain by thousands of tiny workers. Inside these mounds, air flows through a network of passages that channel heat and moisture in intricate patterns. Each insect follows simple rules. It carries soil to locations that feel too warm or too damp, removes material where air seems stagnant, and responds to subtle changes in scent and temperature. From these countless small actions, a ventilation system appears that keeps the inner chambers close to ideal conditions for the growing colony. The mound adjusts over time as seasons shift, with new channels opening and old ones closing. No architect holds the plan in its mind. The structure emerges from constant feedback between insects and environment. In effect, the mound behaves like a self-tuning device that measures and balances the climate using nothing more than instinctive behavior woven together at immense scale. Infants show signs of statistical reasoning before they understand words. Even in the first months of life, human babies track regularities in their surroundings with surprising precision. When they watch shapes appear in patterns or hear streams of syllables, their gaze and attention reveal that they sense which combinations are common and which are rare. Experiments show that when an event violates these emerging expectations, their eyes linger slightly longer, as if something in the scene does not quite fit the forming model in their minds. They have no vocabulary, no formal training, and no explicit grasp of numbers. Yet, their brains quietly tally how often certain sounds follow others, how frequently lines move in particular directions, and how objects tend to interact. This sensitivity helps them separate meaningful units in language, recognize familiar arrangements in the world, and learn where to focus curiosity. Long before a child can describe a pattern, the nervous system is already measuring it, laying foundations for later reasoning with a patient and continuous internal count. Jellyfish without brains still exhibit behaviors that look strangely like learning. In open water, translucent bodies pulse with a rhythm that seems simple at first glance. However, when some species repeatedly encounter obstacles or experience particular lighting conditions, their movements begin to change in a lasting way. The networks of nerve cells spread through their bells and tentacles respond differently after prior exposure, adjusting pulse strength and timing so that collisions become less frequent and paths more efficient. There is no central control center directing this adaptation. Instead, rings of connected cells store traces of recent events in temporary changes to their responsiveness. These traces influence later activity, creating a primitive form of experience dependence. When conditions shift again, the patterns of activity shift with them. The organism behaves as if it has taken something from the past into account. This suggests that the roots of learning reach back to very simple bodies where nervous systems are still more web than organ, and plasticity begins as slight changes in how signals ripple through living tissue. The brain compresses vast amounts of information into tiny neural sparks. Every moment, light, sound, smell, touch, and internal sensation arrive in sprawling detail. If the mind tried to store all of this in full resolution, thought would freeze under its own weight. Instead, chains of neurons transform the flood into compact codes. Groups of cells fire together in patterns that summarize edges, movements, textures, and meanings. Many details vanish, but the important relations remain. A familiar face reduces to a particular constellation of activity. A remembered route becomes a sequence of compressed steps that can later unfold into a clear mental journey. This compression is not simple shrinking. It is clever selection, preserving information that supports prediction and action while discarding background noise. When you recall an event, a relatively small spark of activity in key regions can reconstruct sounds, feelings, and images with surprising richness. Intelligence depends on this ability to pack experience into efficient symbols so that the mind can move quickly through thought instead of drowning in raw sensation. Wolves coordinate hunts through subtle movements that function as tactical messages. Across snowy plains or forest clearings, groups of wolves move with an uncanny sense of shared purpose. They rarely need loud sounds to coordinate. A shift of ears, a brief pause, or a change in the angle of approach can signal an entire adjustment in strategy. Each member watches the others constantly, tracking position and speed. As prey veers one way, a wolf on the opposite flank may quicken its pace or angle outward, prompting companions to close ranks. These small movements carry meaning because they occur within a history of repeated hunts. Young animals learn by following older ones, absorbing the significance of each posture through outcome. Over time, the pack builds a library of patterns, each corresponding to a particular configuration of terrain, wind, and target. Without formal planning, the group behaves like a team executing a practiced playbook, turning individual perception into collective action that can overcome even strong and agile prey. Human foresight emerges from brain areas that first evolved for social behavior. Regions that now help you picture next week, next year, or the distant future began as tools for tracking other minds. Early humans needed to remember who helped and who harmed to anticipate how companions might react and to imagine the consequences of sharing food or withholding it. These demands strengthened circuits that could build inner scenes of events that had not yet happened. Over generations, those circuits expanded their reach beyond immediate social exchanges. The same networks used to imagine a friend's response could now model the outcome of a journey, a new dwelling, or a change in hunting ground. As language grew more complex, these imagined scenes became easier to describe and share, allowing groups to coordinate around futures that existed only in thought. Planning cities, technologies, and cultures draws on neural machinery that once served small bands of foragers, revealing that our sense of tomorrow is deeply rooted in the ancient need to navigate relationships. Coral reefs exhibit collective responses that mirror decision-making in living networks. Beneath warm waves, reefs form intricate frameworks of stone and living tissue. Each coral polyp feeds, grows, and reproduces according to local conditions. Yet, the community as a whole behaves like a single adaptive entity. When water temperature rises or light levels change, chemical signals spread through the reef, prompting shifts in how polyps share nutrients with their symbiotic algae. Some sections may reduce growth to conserve energy, while others ramp up repair to counter damage. These adjustments are not directed by a central leader. They emerge from the sum of local interactions as each organism responds to both its immediate environment and the altered state of its neighbors. The result is a distributed response that can hold a complex system together in the face of stress. In this way, the reef performs something very similar to collective decision-making, selecting beneficial strategies through countless small acts of physiological negotiation. Your mind predicts other minds by simulating them using pieces of itself. When you watch someone frown, hesitate, or light up with excitement, your own neural circuits quietly echo those expressions. Brain regions involved in your feelings and actions activate as if you were experiencing a softened version of what you observe. Using these echoes, the mind assembles an internal portrait of another person's perspective. It borrows its own patterns, then reshapes them to fit the hints it can see. Experience refines this process. Every conversation, conflict, and moment of connection adds detail to the internal models you carry. Over time, you learn to sense when someone is confused, guarded, honest, or hiding distress, even without explicit signals. This capacity to simulate others supports trust, cooperation, teaching, and the subtle dance of everyday interaction. It is a form of intelligence that depends on using the self as raw material for understanding those who stand outside the self. Some monkeys understand fairness and protest when they see unjust treatment. In groups that share food, grooming, and protection, certain monkeys track how rewards flow between individuals. When two companions perform similar tasks and one receives a sweeter or more desirable item, the other may refuse its own lower quality reward, turn away from the giver, or display clear agitation. This reaction costs something in the short term since rejecting food offers no immediate benefit. Yet, it sends a powerful signal. By reacting strongly to uneven outcomes, the animal asserts an expectation that cooperation should bring roughly balanced returns. Over repeated interactions, such responses can discourage exploitation, encouraging more even treatment within the group. Young monkeys observe these exchanges and gradually adopt similar standards, absorbing a sense of what counts as acceptable sharing. This early form of fairness does not rely on formal rules or language. It arises organically from the pressures of living closely with others where long-term stability depends on mutual regard rather than simple dominance. AIs can discover mathematical patterns that no human has ever described in words. When modern learning systems sift through enormous fields of shapes, sequences, and numerical structures, they move through spaces far too vast for human intuition to grasp. These systems test combinations that would take human researchers entire lifetimes to explore. As they do, they uncover hidden regularities within equations, curves, and symbolic expressions. Some of these newly revealed structures point to relationships between mathematical objects that no researcher had ever imagined. Human mathematicians can then examine these discoveries and translate them into formal reasoning, expanding the boundaries of the field. In this way, artificial systems become powerful companions in the search for deeper order. They highlight surprising symmetries, reveal unexpected shortcuts, and expose new layers of structure in long-studied problems. Their discoveries remind us that mathematics contains landscapes so large that only an intelligence capable of tireless exploration can illuminate their most distant corners. Human intelligence may depend on brain cells that move electrical signals like whispered secrets. Hidden within the brain's elaborate web of tissue are cells that shape electrical signals with delicate control. They guide impulses along winding routes, soften them, strengthen them, redirect them, or slow them in ways that alter how thoughts unfold. These cells weave subtle patterns that determine how memories link, how attention shifts, and how meaning emerges from sensation. Their behavior resembles a quiet language spoken between neurons, a language made not of words but of faint changes in voltage and timing. By adjusting the flow of these signals, they create layers of nuance in every thought. They help the brain transition between stillness and lively activity, between emotion and clarity, between habit and insight. Without this population of guiding cells, intelligence would become rigid and shallow. Instead, their constant shaping of electrical activity enriches the mind, allowing creativity, flexibility, and depth to thrive. Certain fish recognize themselves in mirrors and adjust their behavior accordingly. In clear water where reflections shimmer like shifting windows, a few species of fish demonstrate a remarkable awareness. When they encounter their own mirrored image, they respond in ways that indicate recognition of self rather than confusion with another animal. If a visible mark is placed on their body, they attempt to remove it after seeing it in the reflection, as if they understand that the mark belongs to them. This behavior requires more than simple visual processing. It demands an internal model of the self, a sense of personal boundaries, and an ability to distinguish inner experience from the outside world. These fish adjust their posture, inspect themselves repeatedly, and behave with intention rather than instinctive reaction. Their actions reveal a depth of cognition that challenges assumptions about where self-awareness begins. In the quiet flicker of a mirror, a mind discovers itself. The mind identifies patterns by creating stories even when none exist. When confronted with scattered details, the mind instinctively forms connections, turning fragments into coherent shapes and meanings. This tendency emerges from ancient survival needs. Early humans benefited from sensing structure in the environment even when the structure was faint. Over time, the brain became specialized for weaving elements into narratives that explain what might be happening. This can lead to false impressions, but it also fuels creativity, imagination, and interpretation. When people see shapes in clouds, find rhythm in random sounds, or draw meaning from coincidences, they are witnessing this narrative instinct at work. It helps the mind compress complexity into forms that feel understandable. It provides emotional coherence and guides decision-making. Although it can mislead, it also drives curiosity and exploration. The mind makes sense of the unknown by shaping it into a story that feels whole. Bats use social learning to share new feeding strategies across entire colonies. Within dark roosts and moonlit skies, bats pass knowledge from one individual to another through close contact and shared experience. When a single bat discovers a new food source or an unusual way to extract nourishment from a challenging fruit, others observe and mimic the behavior. Over time, an entire colony can adopt the new method, turning a single innovation into a shared tradition. This transmission depends on trust, memory, and the ability to map another's actions onto one's own movements. Younger bats pay special attention to experienced adults, following them during foraging flights and repeating behaviors until they master the technique. Through this process, colonies adapt to changing environments with agility. Feeding strategies become part of a cultural inheritance passed not through genetics, but through living demonstration. Human curiosity expands when the brain encounters something it cannot predict. When the mind meets a situation that does not match expectation, a spark of heightened attention ignites. Neural circuits become more active, absorbing detail with greater sensitivity. This surge of interest encourages exploration, allowing unfamiliar information to flow into memory more deeply than routine events. Curiosity grows in this gap between what is known and what feels just out of reach. It pushes the mind to investigate, compare, experiment, and reorganize understanding. These moments often shape lifelong interests, guiding people toward fields of study or creative passions they might never have pursued otherwise. The brain thrives on novelty because it expands the range of possible ideas, revealing new paths through the world. Curiosity becomes both a compass and a fuel, pulling the mind forward whenever the horizon shifts. Slime molds solve mazes through a form of memory stored in their shifting shape. Despite lacking neurons, slime molds navigate complex environments with surprising intelligence. When placed in a maze with a food source positioned at the exit, the organism spreads through every available path. Over time, it withdraws from dead ends and reinforces the route that leads to nourishment. This process resembles memory, not stored in cells, but in the changing geometry of the organism itself. Each stretch and retreat leaves subtle chemical traces that influence future movement. As the slime mold reshapes its body, its shifting form records which paths are useful and which are not. The result is a dynamic map etched into living tissue. Through continuous growth and retraction, the organism learns and remembers without a brain, revealing that intelligence can arise from the simplest materials when organized in the right way. The brain builds maps of the world using rhythm, like an internal song. Deep within the brain, networks pulse with repeating patterns that act like a silent melody, guiding perception and movement. These rhythmic cycles help organize spatial information, allowing the mind to track locations, distances, and boundaries. As you walk through a room or move along a familiar road, these internal rhythms synchronize with sensory input, creating a stable map that persists even when vision is limited. They provide a scaffold for memory, helping you recall where objects lie, which paths you have taken, and how far you have traveled. These internal songs shift subtly as you change pace, direction, or goal, adjusting the mental representation of space. Without these continuous pulses, navigation would become disordered and unstable. The rhythm gives the world structure inside the mind. Large predators teach their young through lessons that resemble apprenticeships. In grasslands, forests, and icy tundra, young predators learn not through instinct alone, but through guided practice. Adults demonstrate stalking, chasing, and the precise timing needed to bring down prey. They allow juveniles to attempt difficult tasks while staying close enough to intervene if danger arises. Each lesson offers new challenges, gradually building skill and confidence. Young animals study every movement, absorbing how to read wind direction, how to approach without sound, and how to coordinate within a group. These sessions continue long after the young can walk and hunt in basic ways, showing that mastery requires more than instinct. It requires mentorship. Knowledge passes through generations as lived experience rather than fixed programming, giving each new cohort a richer foundation for survival. Human language may have emerged when our ancestors learned to manipulate symbols for fun. Before words carried meaning, early humans likely experimented with sounds, gestures, and marks simply because they found joy in play. These playful acts created patterns that companions began to recognize and repeat. Over time, certain sounds gained consistent associations with common objects or actions. As these associations solidified, groups developed shared symbolic systems rooted in joy, curiosity, and creative exploration. Play allowed individuals to test new forms of expression without fear of error. It encouraged imitation, variation, and elaboration. Gradually, these simple symbolic experiments grew into richer forms of communication. From casual mimicry emerged structure. From shared pleasure emerged understanding. Language may have begun as a form of imaginative play long before it became the tool that carries thought across generations. Certain spiders plan hunting routes that require multiple sequential decisions. When these spiders explore complex terrain, they inspect branches, leaves, shadows, and angles long before making their move. Instead of relying on instinct alone, they pause to study the environment, evaluating which path will place them in the best position for an ambush. Their movements shift from quick exploration to deliberate planning as they test surfaces, backtrack, and reposition themselves with notable purpose. Once a route is chosen, they commit to it with steady precision, even if it requires several steps before reaching a vantage point. Some individuals will inspect an area, retreat to a hidden spot, and later return to follow a path they selected earlier. This reveals an inner process that stores temporary information about location, distance, and opportunity. Their ability to coordinate multiple moves without external cues suggests an unexpected depth of organization. In the quiet world of leaves and webs, these spiders make decisions that unfold like miniature strategic plans. Your brain understands motion before it recognizes the objects that are moving. As soon as something shifts in the environment, specialized pathways in the visual system react to the change even before the brain identifies what is moving. This rapid sensitivity to motion comes from ancient neural circuits that evolved to detect predators, prey, and other crucial events. These circuits respond to direction and speed with astonishing speed, allowing the mind to prepare for action before conscious recognition forms. Only after this first wave of activity does the brain piece together shape, texture, color, and identity. This separation gives humans a powerful advantage. Motion sets the stage, drawing attention to areas that matter, guiding gaze and sharpening perception. This early processing influences decisions, emotions, and expectations, shaping how a person responds to the world. The deep layers of the visual system reveal that understanding movement is not a refinement of sight, but one of its earliest and most fundamental purposes. Apes create tools in ways that reveal their ability to infer hidden mechanisms. When apes shape sticks, adjust branches, or modify stones, they often behave as though they understand the invisible forces that make these objects effective. They test weight, length, and flexibility, discarding tools that fail to match the demands of the task. This shows they are not simply copying learned patterns, they are reasoning through the problem. In experiments, they will choose tools that can reach beyond their direct grasp, alter objects to improve leverage, or combine materials to create shapes they have never seen before. These actions suggest that apes can imagine how a tool will behave before using it. Their choices reveal an understanding that certain hidden properties, such as strength or tension, influence results. This ability forms a link between animal cognition and early human invention. It shows that the foundations of technological thought run far deeper in evolutionary history than once believed. Human insight often appears when the brain switches into a metastable neural state. Inside the brain, countless networks hum with their own rhythms. When an insight emerges, the system briefly enters a fluid condition where these rhythms loosen, reorganize, and reconnect in unusual ways. This state lies between order and chaos. It is not fully stable yet, not disorderly. During this delicate moment, information that was stored in separate regions can suddenly interact, creating new relationships that the mind had not considered before. People often experience these moments as sudden clarity. A problem that felt impossible becomes simple. A connection that once seemed hidden becomes obvious. This shift does not result from direct effort. It comes from the brain allowing itself to move into a flexible arrangement where ideas can reorganize freely. Once the insight forms, the system settles again, holding the new understanding in a more stable pattern. Insight arises from the brain's ability to briefly relax its normal boundaries and explore new internal configurations. Birds with tiny brains can perform logic tasks once thought impossible without a cortex. Despite their small size, the brains of certain birds contain densely packed neurons arranged in highly efficient networks. These structures allow them to reason about relationships, understand cause and effect, and perform tasks that mirror logical decision-making. Experiments show that some birds can identify whether items match certain rules, choose correct options from multiple alternatives, and even understand basic relational concepts. Their success does not come from mimicry alone. It emerges from internal processes that track patterns, test hypotheses, and evaluate outcomes. These birds solve problems using strategies that reflect structured reasoning. Even though their brains lack the layered cortex seen in mammals, this discovery challenges long-held assumptions about how intelligence is built. It shows that thinking does not depend on size, but on organization, density, and the way networks connect. In the flutter of wings and the tilt of a small head, powerful cognition reveals itself. Some coral polyps share nutrients in patterns that resemble resource planning. On the surface, a coral colony appears simple, but deep within its living tissue lies a complex network of exchange. When light, temperature, or nutrients shift, individual polyps adjust how they store and release energy. Some transfer resources towards sections of the colony that require urgent support, such as areas recovering from damage or portions that receive less sunlight. Others temporarily reduce their own demands to stabilize the whole. These transfers follow patterns shaped by internal signals, environmental feedback, and interactions between polyps. Over time, the colony behaves like a system, making choices about distribution, investing where the return will be greatest for survival. This coordinated sharing reveals a distributed intelligence built from simple units working in harmony. It shows how life can plan without a central planner, using communication and cooperation to maintain balance in the shifting underwater world. Human genius often emerges from the ability to combine unrelated ideas. When the mind encounters two concepts that appear to have nothing in common, a unique cognitive process begins. Instead of rejecting the mismatch, human intelligence often blends the ideas, forming new structures that did not exist before. This combination can generate inventions, stories, theories, or insights that feel astonishingly original. Genius thrives on these unexpected unions. The brain searches for hidden links, allowing memories, emotions, and abstract thoughts to mix. This mixing does not follow a predictable formula. It grows from curiosity, flexibility, and a willingness to explore unfamiliar mental territory. Many breakthroughs in science, art, and philosophy have emerged from this ability to cross boundaries. Genius is not a single skill. It is a way of navigating thought that welcomes the unusual and embraces the collision of different worlds. Sea lions learn rules of syntax that mirror basic principles of human grammar. During training tasks, sea lions have demonstrated the ability to understand how elements in a sequence relate to each other. They can learn that certain symbols must appear before others, that some combinations create meaning while others do not, and that relationships between elements remain consistent even when new symbols are introduced. This ability reveals an understanding of structure rather than simple memorization. When given new arrangements, they evaluate the order and respond correctly only when the pattern matches the rule they learned. Such behavior shows sensitivity to syntax, a foundational principle in human language. Although sea lions do not speak, their ability to process structured relationships highlights a cognitive competence once believed to be uniquely human. Their minds navigate patterns with an elegance that mirrors grammatical reasoning. The brain prunes connections to become smarter by becoming simpler. As the brain develops, it creates far more connections than it will eventually keep. Over time, many of these connections are trimmed away, reducing complexity while strengthening efficiency. This pruning process allows signals to travel more cleanly, thoughts to form more precisely, and responses to sharpen. Instead of relying on sheer volume, the brain refines itself by removing paths that add noise or confusion. This simplification supports learning, memory, and reasoning. It helps the mind focus on what matters while discarding what slows it down. Pruning continues throughout life, guided by experience, practice, and changing needs. Intelligence thrives not because the brain grows endlessly, but because it becomes an elegant network shaped by what each person encounters. Some primates teach cultural traditions that persist across generations. In several primate communities, individuals pass down behaviors that reflect shared culture rather than instinct alone. Elders demonstrate techniques for finding food, preparing materials, or resolving conflicts. Young members watch closely and practice until they master each tradition. These behaviors differ from one group to another, even when the groups live in similar environments, showing that the knowledge is learned rather than inherited. Over time, these traditions evolve, gaining new variations or subtle refinements. They form collective identities that shape how groups behave and cooperate. This cultural transmission reveals a level of intelligence grounded in community and memory. It shows that cognition is not only an individual trait, but a shared resource carried across lifetimes through the stories and practices of a group. Human intelligence may grow when we confront ideas that contradict our beliefs. When a familiar viewpoint is challenged, the brain shifts into a heightened state of evaluation that strengthens cognitive flexibility. This encounter with contradiction disrupts automatic thinking and forces deeper examination of assumptions that often remain invisible. As the mind works to integrate conflicting information, neural networks that usually operate separately begin to interact more vigorously. These interactions create new pathways that expand how a person understands the world. Over time, repeated exposure to ideas that push against comfort zones encourages the development of more nuanced reasoning. Emotional regulation also improves because the mind learns to remain steady even when faced with perspectives that feel disorienting. This process strengthens intellectual resilience and supports growth in fields requiring creativity, open-mindedness, and critical thought. Confronting contradiction does not weaken understanding. It enriches it by prompting the brain to refine and reorganize what it knows. Ants use chemical communication networks to optimize foraging routes in real time. In a bustling colony, ants move across the ground, leaving trails of faint chemical signals that accumulate into a dynamic map of opportunity. Each ant follows portions of this map, adding new information as it travels. When a rich food source is discovered, the concentration of chemical markers increases rapidly along that path. As more ants follow it, the trail becomes stronger and more efficient. When the resource declines, fewer ants reinforce the route and the signal begins to fade. This continuous updating creates a form of collective intelligence in which the colony adapts instantly to a changing environment. No single ant understands the entire map. Instead, each individual responds to local cues, contributing its movement to a living flow of information. This decentralized strategy allows the group to solve complex optimization problems with elegant simplicity. In the silent exchange of scent, ants build shared knowledge that guides the entire colony towards success. The brain represents concepts as clouds of activity rather than precise locations. A concept in the human mind is not stored in a single place. Instead, it exists as a shifting constellation of neural activity that changes depending on context, emotion, and sensory input. When a person thinks about an idea, clusters of neurons in several regions activate at once, each adding a unique component. Some regions contribute sensory impressions. Others contribute emotional tone, memory associations, or abstract structure. Together, they form a cloud-like pattern that the brain can reshape as experiences accumulate. Because these clouds overlap, concepts can blend, influence one another, and inspire new connections. This distributed form of representation allows remarkable flexibility. It explains how a familiar idea can feel entirely different in a new situation. It also reveals why creative thinking feels expansive, as if the mind is navigating landscapes rather than retrieving fixed entries from a mental archive. Otters pass down tool use techniques through memory and observation. Along coastal shorelines, otters float on their backs with stones balanced on their chests, striking shells with rhythmic precision. Young otters watch these actions with intense focus, observing how adults select the right stone, position it comfortably, and apply just enough force to open stubborn shells. Eventually, the young begin to imitate these movements, experimenting with stones of different weights, adjusting their grip, and learning to strike at effective angles. These lessons become part of family identity, as certain groups favor particular stones or develop distinct ways of cracking open different kinds of prey. Over generations, such practices evolve into long-lived traditions. This passing of knowledge demonstrates a cognitive capacity for cultural inheritance. The techniques survive not through instinct, but through shared memory and observation, revealing a level of learning that binds otter communities together. Human imagination works by blending memories into patterns that have never existed. When a new idea forms, the mind gathers fragments from past experiences and arranges them into shapes that defy direct memory. A scent from early childhood may connect with a scene glimpsed on a distant journey. An emotion from a conversation might combine with the image of a place only visited in dreams. These fragments merge to create possibilities that feel fresh and compelling. This blending process relies on networks that bridge sensory memory, emotional learning, and abstract thought. Imagination becomes a space where the past transforms into new patterns that never existed before. It allows people to envision inventions, stories, solutions, and futures. By drawing on its deep reservoir of lived experience and reorganizing it through boundless creativity, the mind constructs entire worlds that live only in thought. Manta rays show signs of curiosity that resemble introspective awareness. As manta rays glide through warm ocean currents, they sometimes approach unfamiliar objects or reflective surfaces with an unusual degree of attentiveness. Instead of responding with fear or aggression, they circle slowly, adjusting their angle and distance as though examining details intently. When encountering reflections, some individuals engage in movements that appear exploratory rather than territorial. Their gentle turns and pauses give the impression that they are studying their own appearance or testing how the reflection responds. In the open sea, they also investigate new shapes, lights, and textures with sustained interest. This behavior suggests more than simple attraction to novelty. It hints at a deeper form of curiosity in which the animal explores not only the environment but its own presence within it. The calm and deliberate nature of their actions reflects a quiet intelligence that remains largely mysterious. The mind learns complex skills by running internal simulations over and over. Before performing a skill in the physical world, the mind often rehearses it internally. These mental rehearsals activate many of the same neural circuits that support actual movement, allowing learning to occur even in complete stillness. A musician may silently practice passages while lying down. An athlete may imagine a sequence of steps while resting. A speaker may run through words without moving the lips. Each rehearsal strengthens connections that guide timing, coordination, and precision. Over time, the simulated action becomes more refined, preparing the body and mind for smooth execution when the real moment arrives. This internal rehearsal is a powerful learning tool because it allows limitless repetition without fatigue or risk. It transforms imagination into a form of silent practice that accelerates mastery. Social insects exhibit group memory stored in the movements of the entire colony. In colonies where thousands of insects interact, memory does not reside in individuals, but in the collective flow of behavior. When conditions change, the entire colony shifts its movement patterns in response. If a threat appears, workers adjust their pace and direction, creating a recognizable pattern that persists long after the event. During productive times, the rhythm of activity becomes faster and more synchronized, forming another distinct pattern. These collective motions serve as traces of experience that guide future responses. The colony remembers not through personal recall, but through coordinated action. Every movement reinforces or alters the shared pattern, turning the entire colony into a living record of events. This distributed memory allows the group to navigate challenges with precision that no single insect could achieve alone. Creative insight often emerges when the brain temporarily reduces executive control. When the systems responsible for discipline and focused attention relax, the mind gains access to a wider range of associations. Ideas that normally remain separated begin to drift toward one another, forming unexpected connections. This shift allows distant memories, subtle impressions, and imaginative fragments to merge. Creative insight arises when these elements align in a novel and meaningful way. People often experience such moments during restful activities such as walking, bathing, or drifting into sleep when external demands fade. During these intervals, the brain explores without pressure, embracing possibilities that rigid focus would block. Once the insight appears, executive control returns, stabilizing the new idea. Creativity flourishes in this interplay between looseness and structure, where freedom opens the door and discipline shapes the result. Certain crabs navigate using celestial cues like tiny astronomers. On coastal sands beneath open sky, certain crabs orient themselves using patterns of light that filter from above. They detect the position of the sun and the subtle polarization of sunlight reflected across the landscape. Even when clouds obscure the sky, they read faint gradients that reveal the hidden direction of daylight. These cues allow them to travel long distances with reliable accuracy. As they scuttle across beaches and tidal zones, they adjust their path based on shifting celestial information, navigating with precision that seems astonishing for such small creatures. Their reliance on sky-based guidance shows a remarkable ability to process complex environmental signals. In their tiny bodies lies a form of natural astronomy that allows them to move confidently through a world shaped by tides, shadows, and the slow sweep of the heavens. Human learning strengthens when surprised by information that violates expectation. When something happens that does not fit what the mind predicted, a quiet alarm rings through the nervous system. Circuits involved in attention, error detection, and memory light up together. This moment of surprise pushes the brain to stop gliding along old habits and instead examine the new event in sharper detail. Neurochemicals that support learning rise, marking the experience as important. The mind begins to compare the unexpected fact with older knowledge, searching for a way to fit it into a larger pattern or, when needed, to reshape the pattern itself. Lessons linked to surprise are stored more deeply and recalled more easily because they carry the imprint of emotional and cognitive urgency. Over time, a life filled with gentle, repeated surprises builds a mind that updates itself more readily, that stays flexible, and that remains open to correction instead of clinging to comforting illusions. Robots using self-organized learning develop strategies humans never considered. In complex environments where outcomes depend on many interacting factors, self-organized learning systems explore possibilities in ways human designers could not plan in advance. Engineers set basic rules and goals, then allow the machines to adjust their own internal parameters through trial, error, and feedback. Given enough time and variation, these systems discover approaches that appear alien to human intuition, yet perform remarkably well. A robot might learn to move in a strange gait that looks inefficient but conserves energy over long distances, or it might rearrange its own sequence of actions to exploit tiny details in its surroundings. Researchers studying these solutions often find that the strategies obey principles that were invisible before the machine uncovered them. In this way, self-organized learning turns robots into collaborators in discovery, expanding the space of possible behaviors beyond what any single human mind could imagine alone. The brain encodes spatial knowledge through firing patterns that act as internal coordinates. As you move through a room, walk along a familiar path, or turn a corner in a city, specific groups of neurons fire in patterns that map where you are and how you are oriented. Some cells become active when you occupy a particular location. Others respond to the direction you are facing, or the boundaries around you. Together, they form an internal grid that tracks position within the environment. This grid does not use physical measurements like a drawn map. It uses rhythms and sequences of activity that shift as you move, maintaining a stable sense of space inside a constantly changing world. When you later recall a route, these patterns replay in altered form, guiding your memory of where to turn and how far to go. Spatial knowledge lives not as a picture, but as a living choreography of electrical pulses that traces the world within the brain. Primates use social strategies that resemble elementary political reasoning. In groups of monkeys and apes, individuals do more than react to dominance and submission. They track alliances, trade favors, and manage reputation in ways that look strikingly like simple politics. A primate may groom one partner to secure support in a future conflict, or it may choose to back a particular ally at a critical moment, strengthening a bond that will later provide protection. Some individuals reconcile after fights with gestures that restore trust, aware that long-lasting hostility weakens both sides. Others quietly observe tensions and choose when to intervene, gaining influence without taking constant risks. These behaviors require memory for past interactions, the ability to predict how others will respond, and a sense of how relationships combined to shape group stability. In the shifting web of glances, gestures, and coalitions, an early form of strategic social thinking emerges that foreshadows human negotiations and alliances. Human intelligence may rise when we engage with ideas just beyond our understanding. When a concept is neither easy nor impossibly difficult, it occupies a sweet spot where the mind must stretch to grasp it. In this zone, effort feels demanding but not hopeless. The brain recruits additional resources, bringing working memory, attention, and reasoning into closer coordination. As it struggles to follow the new idea, it forges connections between existing knowledge and the unfamiliar structure in front of it. Each partial success reinforces motivation, while each partial failure reveals gaps that can be bridged with further exploration. Over time, repeated engagement with material just beyond current ability expands capacity. People who habitually seek out such challenges in art, science, philosophy, or everyday problem-solving gradually build more complex mental frameworks. Intelligence does not grow from remaining inside what is already known. It grows from reaching into the near unknown and pulling pieces of it back into understanding. Parrots form concepts about same and different in ways similar to human children. During carefully designed tests, some parrots can look at pairs or groups of objects and judge whether they match in color, shape, or number, even when the specific items are new. They are not simply memorizing correct responses for familiar combinations, they are applying abstract rules about sameness and difference that hold across many situations. When presented with a fresh set of objects, they can still indicate which ones share a property and which ones do not, showing that they understand a general idea rather than a single example. Human children pass through a similar stage as they learn to classify and compare. Parrots reach this ability through entirely different evolutionary paths using vocal learning, social intelligence, and a powerful curiosity about their surroundings. their minds revealed that the capacity for abstract comparison is not limited to primates, and that the roots of concept formation can appear in feathered brains as well. Neural networks in animals sometimes store long-term memory in their immune systems. In some organisms, the cells that defend the body against disease also carry traces of past experiences that reach beyond pathogens. Immune cells adapt to repeated exposure, and their adaptations can influence how the nervous system responds to stress, trauma, or recurring events. Over time, patterns of immune activity shape the body's baseline state, altering the chemistry in which neurons operate. This creates a subtle record of what an animal has lived through, written not only in synapses, but in circulating cells and signaling molecules. In certain cases, these immune patterns can even affect offspring who inherit a body already tuned by the experiences of previous generations. Memory spreads from brain to blood, from individual life into lineage. Intelligence in this sense becomes a distributed phenomenon linked to how the entire organism learns from the world, not just how its neurons fire. Human conscious awareness emerges only after the brain has already made decisions. When you feel yourself choosing, many processes have already unfolded beneath the surface. Sensory systems have gathered information, emotional centers of weighed values and motor planning regions have begun to tilt toward one action or another. These processes occur rapidly and largely without awareness. Only when they reach a certain stage does the conscious mind experience the sense of deciding. Awareness arrives like a storyteller stepping into a play that has already begun, narrating and sometimes adjusting the outcome, but never starting from nothing. This does not remove the meaningfulness of choice. Instead, it reveals that conscious will is part of a broader layered system, one in which reflexes, habits, and deep evaluations all contribute. The feeling of deciding is the moment when this hidden activity becomes visible to itself, and in that visibility, new possibilities for reflection and change appear. Elephants coordinate movements through vibrations that travel through the ground. As herds move across savannas, elephants send and receive signals that do not travel only through air. Low-frequency rumbles and stomps create vibrations that pass through soil and rock. Sensitive receptors in their feet and trunks detect these tremors, allowing individuals to sense distant movements of companions that may be out of sight. Through this channel, they can coordinate group travel, warn of danger, or guide stragglers without needing constant visual contact. Young elephants learn to interpret these signals by following older members and feeling the faint messages underfoot. Over long distances, this vibrational communication knits the herd into a coherent unit. Even when members are scattered, the ground itself becomes a medium for shared awareness, carrying information between massive bodies that move like a single living network across the land. Human creativity may depend on brain regions that compete and cooperate at the same time. Within the brain, some networks specialize in focus, control, and goal-directed behavior, while others favor imagination, wandering thought, and free association. During creative work, these networks do not take turns so much as they engage in a delicate tension. The imaginative systems generate possibilities without worrying about rules, and the controlling systems evaluate, refine, and select among them. At times they oppose each other as discipline tries to suppress wild ideas, and daydreaming resists constraint. Yet when creativity flows, they achieve a dynamic balance. The open networks roam widely but remain tethered to a sense of purpose. The controlling networks relax just enough to allow novelty, but not so much that thoughts dissolve into chaos. This ongoing dance between cooperation and competition gives creative thinking both structure and vitality, allowing new forms to appear without losing coherence. Cuttlefish remember specific events in a way that resembles episodic memory. In shifting underwater landscapes where the scenery changes with every tide, cuttlefish carry a remarkable form of memory that allows them to navigate uncertainty with subtle intelligence. They retain detailed recollections of places they have explored and distinguish between areas that offered rich prey and those that presented danger. Their memory includes the circumstances of each experience, such as the time of day or the quality of light filtering through the water. When returning to a familiar reef or sandbank, they behave as though consulting an inner timeline, adjusting their behavior based on a combination of location and context. This memory does not operate like a simple catalogue of images. It functions as a flowing record of experiences stitched together across time. It appears to help them predict which hiding places might still be safe, which hunting areas are likely to replenish, and which predators might linger nearby. Even as cuttlefish age, they maintain this capacity with surprising clarity, showing a preservation of memory rarely witnessed in other ocean dwellers. Their intelligence emerges through a fusion of perception, recollection, and anticipation, allowing them to move through complex territory with a confidence shaped by lived experience. The brain uses sleep to strengthen hidden patterns you did not notice you learned. Throughout each day, the brain absorbs countless fragments of information that drift beneath conscious awareness. Words overheard, patterns glimpsed in passing, rhythms sensed during movement, and subtle shifts in tone or expression all settle quietly into neural circuits. When sleep arrives, these fragments awaken within the intricate waves of nocturnal brain activity. During lighter stages of rest, networks replay traces of waking experience, as if sorting through memories gathered earlier. As the night deepens, the brain begins reinforcing the patterns deemed valuable, linking them with related impressions and slowly weaving them into more stable forms. This process strengthens learning that felt vague during the day, turning faint impressions into accessible knowledge. People often wake with improved understanding of concepts that previously resisted clarity. Musicians find difficult passages easier. Language learners speak with smoother rhythm, and problem solvers discover clarity where confusion once reigned. Sleep serves as an unseen teacher, shaping cognitive growth in the hidden hours when awareness fades and internal rhythms carry the mind toward deeper integration. Some fish build intricate structures that reveal geometric understanding. In wide, sandy plains beneath clear water, certain fish create astonishing circular formations composed of ridges and valleys shaped with steady precision. These structures span impressive distances and require sustained effort to maintain. The fish sweep the sand with repetitive motions, adjusting the depth of grooves and carefully managing symmetry. They orient their bodies in deliberate arcs, returning again and again to refine small sections until the entire formation reaches an elegant balance. Although driven by instinct, these creatures exhibit awareness of spatial relationships as they monitor angles, align contours, and correct disturbances caused by waves or drifting sand. The final structure resembles an underwater mandala, functioning both as a display for potential mates and as a demonstration of refined motor intelligence. The fish must hold the blueprint in memory throughout the construction process, maintaining consistent spacing and adjusting each segment in response to changing currents. Their artwork vanishes with time, but its creation reveals a remarkable ability to manipulate geometry through motion alone. Human intelligence emerges from interactions between many tiny brain networks. Within the human brain, countless miniature networks operate simultaneously, each performing a different task. Some monitor sounds and shapes. Others store fleeting impressions for use in the next breath of thought. Still others evaluate emotion, manage planning, construct language, or connect present experiences with past memories. No single network carries the full weight of intelligence. Instead, thought emerges from the shifting alliances formed between these circuits. During moments of reflection, they coordinate their rhythms, exchanging signals that travel through intricate pathways. When a challenge arises, networks that typically work separately may join forces, creating a temporary union that produces novel insight. Once the challenge passes, the networks dissolve back into their usual patterns. This constant formation and reformation of alliances allows the human mind to adapt to changing environments with remarkable speed. Intelligence lives not in isolation, but in the harmony created by countless contributors working in dynamic balance. Certain birds practice songs in their sleep as their brains rehearse for dawn. Young birds learning to sing spend daylight hours absorbing the melodies of adults. These melodies hold social significance, marking territory and announcing identity. As night falls, the forest grows quiet. Yet the learning continues in silence. Within the sleeping bird, neural circuits governing vocalization replay fragments of the day's songs. These internal echoes occur without physical movement, yet they activate the same sequences that control real singing. Through these nocturnal rehearsals, the bird adjusts pitch, timing, and rhythm, gradually transforming scattered notes into coherent melodies. When dawn arrives, the bird awakens with improved command over its voice, shaped by work performed in dreams. This nightly refinement continues for weeks or months, depending on the complexity of the species' song. By the time the bird sings with confidence at sunrise, the melody carries the imprint of countless silent practices woven through many nights of sleep. Problem-solving improves when the brain shifts to using energy-efficient states. When confronting difficult challenges, the mind does not always rely on intense effort. Instead, it often shifts into a quieter mode where neural activity becomes more organized and efficient. This mode reduces unnecessary firing and concentrates resources along pathways most relevant to the problem. In this state, information flows with greater clarity, allowing subtle connections to emerge that would be drowned out during periods of high stress. The mental landscape becomes less cluttered, and ideas that once felt tangled begin to separate into understandable parts. Many breakthroughs occur during moments of calm reflection rather than forceful thinking, because the brain reaches optimal efficiency when tension relaxes. This transition into an energy-saving mode allows complex relationships to surface naturally, reflecting a deeper form of intelligence that depends on harmony rather than strain. Monkeys infer intentions from gestures in ways that mirror early human cognition. Monkeys living in complex social groups observe each other with keen alertness. Every gesture carries possible meaning. A relaxed reach may show peaceful intent. A slight hesitation may reveal uncertainty. A tightening of posture may signal an approaching challenge. Through constant exposure to such cues, monkeys develop a capacity to interpret the motives behind actions. They adjust their own responses based on these interpretations, choosing when to support an ally, avoid a potential dispute, or initiate cooperation. This ability parallels the development of social understanding in young human children who also learn to read intention from motion rather than explicit instruction. For monkeys, this skill strengthens group cohesion, allowing smoother interaction within environments where misunderstanding could lead to conflict. Their perceptive intelligence emerges naturally from lives filled with observation, adaptation, and subtle interpretation. Human thought can momentarily synchronize across people during deep conversation. In certain moments of shared dialogue, two minds fall into an unusual form of harmony. As attention intensifies and emotion aligns, brain rhythms in both individuals begin to follow compatible patterns. This synchrony reflects more than simple agreement. It arises from simultaneous engagement with the same idea, forming a temporary shared mental landscape. During these moments, communication becomes fluid and effortless, as though each person understands the other with heightened clarity. The alignment strengthens when trust deepens or when the conversation touches on meaningful subjects. Although brief, these periods of synchrony reveal the profoundly social nature of human cognition. They show how thought can stretch beyond individual boundaries, forming a bridge between minds through the simple act of genuine connection. Wolves learn social rules by watching conflicts inside the pack. Young wolves grow up immersed in the shifting tensions of pack life. They observe quarrels over food, rank, and territory with unwavering attention. Each conflict teaches a different lesson. They learn who commands respect, who yields gracefully, and how disputes resolve without lasting resentment. They note the postures that signal challenge, the gestures that restore peace, and the timing that determines whether an interaction escalates or dissolves. Through these observations, wolves build a mental framework for navigating their own future roles. They eventually adopt behaviors that maintain harmony, reduce unnecessary violence, and strengthen group unity. Their understanding of social balance emerges gradually, shaped by countless moments of watching, learning, and absorbing the unwritten rules that govern pack stability. Human judgment uses mental shortcuts that often reveal hidden patterns in our environment. Throughout life, the brain learns to recognize subtle regularities in the world. It stores these regularities as rapid-acting mental shortcuts that guide decisions with impressive speed. A slight shift in someone's tone may signal emotional change. A faint environmental cue may reveal a hidden pattern. A familiar structure in a new situation may suggest a likely outcome. These shortcuts do not reflect carelessness. They reflect deep familiarity with repeated experiences. Although they occasionally mislead, they function well in environments that mirror the conditions in which they were learned. They allow humans to act quickly in complex situations where full analysis would be too slow. These patterns reveal how intelligence extends beyond deliberate thought, relying on quiet forms of knowledge accumulated through years of living. Some birds use tools to manipulate fire in a way that suggests causal understanding. Across certain dry landscapes, a few remarkable birds have learned to exploit the destructive power of fire with a level of awareness rarely seen outside primates. When flames sweep through tall grass, these birds wait at the edges for fleeing insects. Yet, their intelligence extends far beyond opportunistic feeding. They sometimes pick up burning sticks, carry them to unburned patches of land, and drop them deliberately into dry brush. The resulting flare sends insects scattering, creating new hunting grounds. For this behavior to work, the bird must predict that a burning fragment will ignite fresh fuel, that flames will move across the grass, and that prey will flee as the fire spreads. It must also handle the ember with care to avoid injury while still placing it where ignition is most likely. This suggests an understanding of cause and effect strong enough to model how fire behaves. Such knowledge cannot rely on instinct alone because the technique changes depending on wind, fuel, and temperature. It is learned through experience, memory, and experimentation within a dangerous element that reshapes the environment itself. Human intelligence may increase when we form mental models of entire systems. When people attempt to understand only isolated details, their thinking remains narrow. Yet when they begin constructing mental representations of entire interacting systems, their intelligence expands in reach and depth. A system can be a forest, a community, a scientific principle, or even the internal workings of a machine. To build such a model, the brain must track relationships among many moving parts, anticipate how changes ripple through the structure, and adjust predictions as new information arrives. This process strengthens areas involved in reasoning, working memory, and abstraction. It also encourages more flexible thinking because systems rarely behave in linear ways. People who habitually form broad mental models grow better at planning, innovation, and adaptation. They detect patterns hidden in complexity and foresee outcomes that escape minds focused only on fragments. By holding entire structures in mind, they allow intelligence to operate across layers of reality rather than within a single point. Primates understand reciprocity and track social debts over years. Within many primate groups, individuals remember who offered support, who shared food, and who withheld help during critical moments. These memories shape long-lasting social strategies. A primate that receives grooming during hardship may later assist the benefactor during a territorial dispute. Another that was ignored in a moment of need may quietly withhold support when the neglectful companion seeks help. These exchanges unfold not through immediate trade, but through long-term tracking of relationships. Individuals monitor fairness, remember past interactions, and adjust their behavior accordingly. This form of reciprocity requires judgment, memory, and the ability to connect past behavior with future decisions. It also requires restraint because the benefits of maintaining social bonds extend far beyond a single encounter. Over years, these remembered debts form the foundation of alliances, peacekeeping, and stability within the group. The intelligence behind these exchanges shows that primates perceive social life as a web of obligations that must be honored to preserve harmony. Human memory strengthens when we connect new knowledge to personal meaning. The mind does not store information with equal weight. Facts learned without context often fade quickly, slipping from awareness as easily as they entered. Yet when new knowledge resonates with personal experience or emotion, memory deepens dramatically. The brain binds the fresh information to existing networks of significance, weaving it into the fabric of identity. This connection activates areas involved in emotion, narrative, and long-term storage, anchoring the new material more firmly. Students who link scientific ideas to personal curiosity retain them longer. Readers who relate characters to their own feelings remember stories vividly. Anyone who ties abstract lessons to lived experience strengthens retention almost automatically. Meaning becomes the thread that stitches knowledge into lasting form. When the mind incorporates information into its sense of self, memory transforms from passive storage into active integration. Certain sharks navigate across oceans using magnetic fields as natural maps. Far from shore, some sharks travel across vast open water with astonishing accuracy, often returning to the same feeding or breeding grounds year after year. They achieve this navigation through sensitivity to Earth's magnetic field. Their bodies contain specialized cells capable of detecting subtle shifts in magnetic intensity and orientation. As they swim, they gather information about the magnetic signature of each region, gradually building an internal representation of the world beneath the waves. This magnetic sense functions like a natural compass layered upon a global map. When currents change or storms disturb familiar routes, the sharks still locate their destinations by referencing the unseen structure of the planet itself. This ability requires more than instinct because magnetic fields vary with depth, location, and time. The sharks interpret these variations, update their internal maps, and adjust their course accordingly. Through this remarkable capability, they navigate an environment with no visible landmarks, guided by an ancient intelligence attuned to the fabric of the Earth. Human insight accelerates when we allow mental rest between difficult ideas. During demanding thought, the mind often reaches a point where further effort produces only confusion. Yet, when people step back, rest, or shift focus, insight frequently appears with unexpected clarity. This occurs because rest allows the brain to reorganize information without conscious pressure. Neural networks that were overloaded during intense concentration begin to settle into more coherent patterns. Hidden relationships among ideas strengthen and irrelevant noise fades. As the mind relaxes, fragments of understanding drift into new configurations, forming structures that were inaccessible during strain. This explains why breakthroughs often happen during walks, quiet moments, or gentle routines rather than at the height of effort. Rest is not the absence of thinking. It is the space in which deeper connections form beyond deliberate awareness. In this softened state, insight arrives naturally, as though rising from the quiet depths of the mind. Orangutans use improvised solutions that reveal flexible foresight. In dense rainforests, orangutans face challenges that demand more than instinctive responses. They often encounter situations involving obstacles, hidden food, or unreachable resources. Instead of relying solely on learned routines, they improvise. An orangutan may choose a branch of a particular thickness to test the stability of a crossing. It may strip leaves from a twig to create a tool for extracting insects or sap. In some cases, it combines several objects to achieve a specific goal, demonstrating an ability to imagine a future outcome and plan toward it. This foresight reflects a sophisticated understanding of cause and effect. Orangutans also adapt their strategies when circumstances change. If a tool breaks, they select a better one. If the environment shifts, they modify their approach. Their improvisation arises from observation, memory, and a flexible intelligence shaped by the complexities of forest life. Human intelligence thrives when diverse ideas interact inside a single mind. Creativity and insight flourish when the mind holds many different kinds of knowledge at once. When ideas from unrelated fields collide, they generate combinations that would never arise from a single discipline. A person who understands art and mathematics may discover patterns invisible to someone focused on only one. Someone familiar with both storytelling and engineering may find solutions that blend imagination with structure. Within the mind, these different domains mingle, compare, merge, and reshape one another. This interaction strengthens cognitive flexibility, broadens perspective, and encourages novel thinking. Diversity of thought becomes a catalyst for innovation because it allows the mind to draw connections across distant regions of understanding. The more varied the internal landscape, the more paths exist for intelligence to travel. Pigeons learn abstract rules that scientists thought required large brains. In controlled experiments, pigeons demonstrate abilities that challenge assumptions about cognitive complexity. They learn to categorize objects not by memorizing individual examples, but by identifying general principles that apply across many variations. They can distinguish patterns involving relative size, shape, or brightness, even when the specific items change each time. These tests reveal that pigeons grasp abstract concepts, applying rules flexibly rather than relying on repetition. Their performance shows that intelligence does not depend solely on brain size, but on the organization of neural circuits. The pigeon brain processes visual information with remarkable efficiency, allowing these birds to understand relationships among objects that appear completely different. This insight forces scientists to reconsider how widespread abstract reasoning may be in the natural world. Human minds evolve through culture, which changes faster than genetics ever could. Human intelligence develops within a cultural environment that transmits knowledge across generations at speeds far surpassing biological evolution. Every individual inherits not only a body shaped by ancestry, but a world filled with stories, tools, symbols, and practices created by countless others. Culture acts as an external memory that extends far beyond the capacity of isolated minds. As people learn from one another, They refine ideas, expand skills, and deepen collective understanding. Cultural evolution allows innovations to spread rapidly, accumulating layer upon layer of shared insight. While genetic changes require vast stretches of time, cultural knowledge transforms within a single lifetime. This rapid exchange shapes how humans think, solve problems, and imagine possibilities. Intelligence becomes a product of collaboration across centuries, woven from the contributions of many minds acting together over time. The brain learns language by detecting tiny patterns in streams of sound. Long before a child understands the meaning of a single word, the brain is already absorbing the rhythm, melody, and statistical structure of the sounds flowing through daily life. As speech washes over the senses, the brain begins identifying repeating fragments, noticing which sounds tend to appear together and which rarely do. This process unfolds automatically without conscious effort, revealing an extraordinary ability to extract structure from complexity. Even in noisy environments, the brain isolates syllables and probabilities, gradually carving boundaries between words that were never presented as separate units. Infants exposed to multiple languages simultaneously keep these patterns distinct, showing that the mind can track several sound systems at once. As learning continues, the brain strengthens connections that represent useful regularities and prunes those that do not. Meaning is layered onto this scaffolding later, built upon an underlying architecture formed through the recognition of subtle acoustic patterns. Language learning therefore begins not with vocabulary, but with pattern detection so fine-tuned that it can transform unbroken sound into a map of communication. Artificial neural networks discover surprising strategies that mirror biological intelligence. When researchers train advanced learning systems to solve complex tasks, these artificial networks often develop solutions no one anticipated. They reorganize information, build internal representations, and sometimes discover shortcuts that resemble strategies found in nature, without being instructed to do so. They cluster similar concepts, compress data into meaningful structures, and form layers of abstraction that help them navigate new situations. In some cases, their internal workings echo patterns seen in animal brains, such as sparse coding, modular organization, and gradual refinement of internal models. These parallels emerge because both artificial and biological systems face similar challenges when interpreting the world. Each must filter noise, detect relevant structure, and form stable predictions. Artificial networks achieve this through vast numbers of simple units working together, while biological networks rely on neurons shaped by evolution. The similarities suggest that intelligence may follow certain universal principles whenever a system must learn from experience, regardless of whether it is made of silicon or living cells. Some insects use vibrations in plant stems as a covert communication system. In dense vegetation where sound and scent easily scatter, certain insects have evolved a form of communication that travels through the structure of the plants themselves. Instead of calling through the air, they create faint pulses that travel along stems and leaves. These vibrations carry information about danger, location, and readiness to mate. Because the signals move through solid material, they are less likely to be detected by predators. Each species shapes its vibrations with specific rhythms and intensities, forming an intricate language that others of the same kind can decode instantly. Some insects even adjust their signals based on wind conditions or plant stiffness, showing a flexible awareness of how physical environments shape communication. Researchers studying these systems discover layers of complexity hidden beneath what appears at first glance to be silent foliage. This covert communication reveals that intelligence can thrive even in tiny bodies when evolution supplies subtle channels for transmitting knowledge. Human thinking improves when we explore questions with no clear answers. When people confront uncertainty, the mind stretches beyond routine patterns. Wrestling with questions that resist simple solutions forces the brain to experiment with new connections and explore unfamiliar perspectives. Instead of relying on well-worn pathways, cognition shifts into a more flexible mode where creativity and insight become more accessible. This process encourages tolerance for ambiguity, strengthens reasoning, and deepens curiosity. Even when no final answer emerges, the act of exploring the unknown expands the mental landscape. Such questions invite reflection, imagination, and the kind of cognitive wandering that supports innovation. They teach the mind to remain open, to consider multiple possibilities, and to recognize that understanding often grows from the search itself. By engaging with uncertainty, human intelligence becomes more adaptive, more resilient, and more capable of uncovering hidden layers of meaning. Primates modify tools in ways that show an understanding of causality. Across various habitats, primates demonstrate a sophisticated grasp of how objects interact with the world. When faced with obstacles that block access to food, they select sticks, stones, or leaves and reshape them to improve their effectiveness. A primate may shorten the branch for better control, sharpen one end to extract insects, or adjust the thickness to increase strength. These modifications reveal an ability to predict how altering a tool will change the outcome of the task. The behavior requires foresight, experimentation, and memory of past successes. It also reflects an understanding that tools can act as extensions of the body, serving as intermediaries between intention and environment. When primates refine these tools, they show more than simple trial and error. They reveal causal reasoning grounded in observation and guided by insight into how the physical world works. Human intelligence often peaks when we collaborate rather than compete. While individuals can achieve remarkable feats of insight, collaboration unlocks forms of intelligence that do not appear in isolation. When people share ideas, critique assumptions, and build upon each other's thoughts, they create an environment where cognitive strengths combine. One person may notice a pattern, another overlooked. Someone else may reframe the problem in a way that clarifies its structure. Through conversation and joint exploration, a group can develop solutions no member would have reached alone. This form of collective intelligence thrives on communication, empathy, and the willingness to integrate diverse perspectives. It also reflects humanity's deep evolutionary history in which cooperation supported survival and shaped the development of complex thought. When minds work together, they create a whole greater than the sum of its parts, revealing that intelligence is not merely an individual trait, but a shared capacity that flourishes through connection. Certain whales learn songs that spread across oceans like cultural waves. In the vastness of the open sea, some whale species produce intricate songs that travel for great distances. These melodies are not fixed, they change through time as individuals introduce new phrases, rhythms, and structures. Other whales adopt these modifications, gradually transforming the song into a shared cultural creation. As migrations bring distant populations into contact, the updated versions spread across thousands of miles until entire regions share a single evolving composition. This cultural transmission requires memory, imitation, and sensitivity to subtle acoustic detail. It also reveals a social intelligence capable of maintaining traditions across enormous distances. Whale song becomes a living artifact shaped by collective creativity, reflecting the dynamic interplay between communication, learning, and social bonding in the ocean's hidden world. Humans think more deeply when surrounded by environments that encourage reflection. The mind responds to surroundings with surprising sensitivity. Natural landscapes, quiet spaces, and environments with gentle sensory input often support deeper thought. In such places, mental noise decreases, allowing attention to settle and ideas to unfold with greater clarity. Reflection becomes easier when the senses are not overwhelmed, giving the brain room to process complex information. These environments help people step back from immediate concerns and consider broader perspectives. They also allow memories and insights to surface that might remain buried in more chaotic settings. Whether walking among trees, sitting near water, or simply resting in a calm room, humans often access richer forms of thought when the world around them becomes quieter. The setting acts as a cognitive partner, guiding the mind toward careful observation and deeper awareness. Some animals show early signs of counting through subtle neural responses, even without language or formal symbols. Some species display primitive forms of numerical awareness. They show distinct neural activity when the number of objects in their environment changes unexpectedly. These patterns appear even in very young individuals, suggesting that sensitivity to quantity emerges naturally rather than through training. Animals may use this awareness to judge group size, identify potential threats, or choose the most advantageous feeding site. The neural signatures reveal that their brains treat numerical changes as meaningful events, responding differently to increases, decreases, and stable quantities. While far simpler than human mathematics, this early numerical sense provides a foundation for more complex reasoning. It also shows that intelligence can arise through basic cognitive building blocks that evolve long before symbolic thought. Human intelligence may be expanding as we integrate with the machines we create. As technology becomes woven into daily life, human cognition evolves alongside it. People extend memory through digital storage, amplify pattern recognition through analytical tools, and explore ideas with computational assistance. These machines do not replace thought. They expand its reach, transforming how humans learn, create, and understand the world. Interacting with technology encourages new forms of problem-solving that blend biological intuition with artificial precision. It also reshapes communication, collaboration, and the pace at which knowledge grows. Over time, this partnership between human and machine forms a hybrid intelligence capable of insights neither could achieve alone. The merging is not physical but cognitive, built through constant exchange between organic minds and the tools they design. As this integration deepens, human intelligence stretches into new territories, reflecting an ever-expanding interplay between creativity and invention. As we drift to the end of this quiet journey through the many shapes of intelligence, allow yourself to feel the soft settling of your mind. You have traveled across oceans and forests and sky. You have wandered through hidden networks of thought within the brain and delicate moments of insight within the natural world. You have followed sparks of understanding as they moved between animals, cultures, machines, and memories. Now everything begins to slow. If you enjoyed this peaceful exploration, I invite you to like, subscribe, or share a thought below. Your support helps more sleepy scholars find this little corner of calm where science becomes a gentle companion to rest. For now, simply breathe. Let your shoulders fall. Let your attention soften. Let the ideas you met tonight fade into a warm glow at the edges of awareness. You do not need to hold any of it. You can let go. The night is here to cradle you. Your mind has done enough. Settle into the quiet. Good night.